So what if the ultimate hard drive isn't made of, perfectly etched silicon, but is instead built out of radioactive waste and frozen light?
I mean, it sounds like science fiction, right?
It really does, but think about the device you're listening to this on right now. You crack open your phone or your laptop, and at the core, you find a solid, tangible architecture.
Yeah, hardware you can actually touch.
Exactly. We are entirely used to data living in microscopic physical boxes, ones and zeros locked into a grid.
But when you step into the absolute bleeding edge of theoretical physics, that solid silicon grid simply melts away.
It really does. You enter a landscape that is fluid, vibrating, and frankly, completely mind-bending. And today, we're doing a deep dive into a theoretical framework so massive and so complex, researchers literally refer to it as a monster.
Yeah, we are jumping into a really fascinating source document today. It's titled Architecture in der Resonanz, which translates to Architectures of Resonance. And the specific framework we're unpacking for you today is called Multicode 6.0.
Which is quite the name.
It is. It's an incredibly ambitious blueprint. It basically attempts to fuse quantum physics, the chaotic behavior of nuclear isotopes, and high-level cryptography into one single high-dimensional system for storing data.
And I think we should establish right up front why anyone would go through the agonizing mathematical trouble of designing something like this.
Right, because it's not exactly easy.
No, not at all. The reality is we are hitting a physical brick wall with our current technology. Classical computing relies on making silicon transistors smaller and smaller to fit more data.
But we've reached a point where those transistors are approaching the size of atoms.
Yeah, and when you get that small, quantum interference kicks in. Those rigid ones and zeros start bleeding into each other, the binary logic just falls apart.
It stops working entirely, so Multicode 6.0 basically stops fighting quantum mechanics. Instead, it asks this brilliant question: what if we just use the natural resonant frequencies of matter itself to hold our information?
So, to understand how you build a storage system out of pure resonance, we have to start with the foundational physics of how movement holds memory.
Exactly. And that brings us to the concept of the harmonic oscillator.
Right.
In classical physics, a harmonic oscillator is just any system that gets pulled away from its resting position and then experiences a force that pulls it back. And that pull is proportional to how far it was moved.
Let's ground that in a physical image for everyone listening. Think of a classical harmonic oscillator, like a kid on a playground swing.
That's a great way to picture it.
Yeah, so if you give the swing a gentle push, it moves a little. If you give it a huge shove, it swings incredibly high. The energy you put into that system is entirely continuous.
Right. The swing glides smoothly through every single inch of the air between its lowest point and its highest point.
But the moment we shrink that swing down to the subatomic level, the rules of reality change.
Totally change. A quantum harmonic oscillator is governed by mathematical methods developed by the physicist Paul Dirac. And what Dirac's math proves is that energy at this tiny scale isn't continuous anymore. It comes in discrete packets, or quanta.
Quanta, right.
Yeah, you can visualize it as like distinct rungs on a ladder.
So updating the playground analogy, a quantum swing is one that magically teleports between specific heights.
Yes.
You can swing at height level 1 or you can swing at height level 2, but you literally cannot stand halfway between those two rungs.
Exactly. The physical space in between those energy levels is forbidden.
So if you're building a hard drive, our data is stored by placing the system onto one of those very specific, well-characterized quantum rungs.
Which fundamentally alters what information storage even means. You aren't just flipping a magnetic switch on a hard drive anymore.
You're doing what exactly?
You are addressing an exact energetic state of a particle.
Wait, hold on. Looking at the fundamental math for this quantum ladder, the lowest possible rung, the ground state, isn't zero.
Right, it's not.
There's this concept of zero-point energy, meaning even at its absolute lowest energetic state, the particle never truly stops vibrating.
It's always moving a little bit.
So if our teleporting quantum swing never actually stops jittering, even when it's totally at rest, aren't we essentially trying to build a hard drive that comes preloaded with static noise?
That's a really good point.
Like, how can you store pristine data on a system that is constantly shaking?
Well, that inherent noise is a massive hurdle, and it's mathematically accounted for in the source as the absolute lower limit of information density.
Meaning you can't get rid of it.
Right, you simply cannot have a perfectly quiet quantum system But the researchers don't try to silence the jitter, they essentially organize it.
Organize the noise.
Yeah, they bypass the chaos by utilizing what are called coherent states.
Okay, so how do you force a jittery quantum particle into a coherent state?
By using extreme precision lasers. Researchers fire ultra-fast femtosecond lasers at diatomic molecules.
Like hydrogen gas.
Exactly, like hydrogen gas, where two atoms are bound together. These laser pulses force the vibrating atoms to synchronize.
Oh, wow.
They essentially bundle the quantum uncertainties together, minimizing that erratic behavior and making the system behave almost classically.
That's wild.
By forcing this rhythm, they create a highly stable phase dimension, so they can start encoding data into the synchronized timing of the vibrations, riding right on top of that underlying zero-point noise.
So it's like trying to transmit a pristine audio signal, but instead of fighting the static on the radio dial, you actually use the rhythmic pulse of the static as the carrier wave for your song.
That is exactly what they're doing. And plus, because we're operating in a quantum state, the particles can cheat physical reality. They can undergo quantum tunneling.
Oh, right. Tunneling.
Yeah, it's one of the most counterintuitive phenomena in physics. Particles can occasionally pass straight through solid potential barriers.
So a wall that would completely bounce back a classical object is basically permeable to a quantum particle.
Yes, and in Multicode 6.0, that tunneling effect is flipped from a physical limitation into a communication feature.
Really?
Yeah, it theorizes using quantum tunneling to transfer data between storage cells entirely without physical wires.
Okay, so to recap where we have a theoretical quantum hard drive that constantly jitterbugs at rest and wirelessly beams its data through solid walls.
Correct.
It's a brilliant concept.
Yeah.
But if we leave it in the abstract math, that jitter eventually shakes the data apart. We need an anchor, right?
We do. We need a physical substrate with an incredibly complex, heavy internal rhythm to hold this code.
And this is where the researchers pivot to something completely unexpected. They dive into the messy, radioactive world of nuclear isotopes.
Right. Moving from abstract theory to the actual hardware, the absolute star of the show in this document is a specific isotope known as samarium-151.
And you listening probably recognize the name samarium-151, or at least its reputation. It is famously known as a radioactive byproduct of nuclear fission.
Yeah, it's literal nuclear waste pulled out of reactors.
And it has a half-life of about 90 years.
The researchers focused on samarium-151 because of its unique architecture. It has a highly deformed, football-like atomic nucleus.
Go.
They run these complex statistical simulation codes programs named Empire and ESIS to model exactly how this specific nucleus absorbs neutrons across massive energy scales.
Massive.
All the way up to 20 mega electron volts.
Wow.
And when they bombard this deformed nucleus, they observe two really mind-bending collective phenomena.
Right. The text highlights the scissors mode and the low energy upend.
Let's look at the scissors mode first, which triggers at around 3 mega electron volts.
Okay, what happens there?
Well, in a normal atomic state, the protons and neutrons exist in a relative balance. But in this state, the entire collective distribution of protons in the nucleus begins to oscillate violently against the distribution of neutrons.
They're swinging against each other.
Yeah, they swing back and forth across each other, mimicking the crossing blades of a pair of scissors.
That's a great visual.
And alongside this, you get the low energy upend, which is an unexpected massive spike in the strength of gamma rays being emitted at very low energies.
I picture the scissors mode, like a symphony orchestra descending into organized chaos. Like, normally the whole orchestra plays the same piece of music.
Right.
But suddenly, the string section representing our protons and the brass section representing our neutrons start playing entirely different battling rhythms.
That's exactly it.
But because they're locked inside the exact same concert hall of the nucleus, the friction between their battling rhythms creates an incredibly dense, specific resonance.
Yes.
But this is where I get completely stuck.
What's the issue?
Well, samarium-151 is radioactive. It is literally falling apart, slowly decaying over 90 years.
True.
If we're building the ultimate data storage system, why on earth would we base it on a foundation that is physically rotting away? The text explicitly compares it to zirconium-96, which is totally stable.
It is stable. Yeah.
So why not just build the hard drive out of stable zirconium?
It seems entirely counterproductive until you look at the density of the data. If you use zirconium-96, yes, your hardware is perfectly stable, but its energy dependencies are relatively flat.
Like a blank slate.
Exactly. From an information standpoint, it's a blank piece of paper. Samarium-151's instability, combined with that deformed nucleus, creates a hyperdense, incredibly complex resonance structure.
Oh, I see.
It's a three-dimensional landscape of vibration. By using it, the researchers can encode data on three distinct levels simultaneously.
Unpack those three levels for us.
Sure. First, you have the isotope level, the foundational choice to use the highly reactive samarium. Second, you have the single particle level. You can excite very specific individual energetic states within the nucleus.
Okay, that's two.
And third, you have the collective level. You can trigger that massive scissors mode to enact large-scale system changes. You're trading long-term elemental stability for an unprecedented cavernous depth of data storage.
Okay, so we have our quantum theory, and we have our wildly complex radioactive nuclear hardware. But if we just start throwing data at a decaying, battling nucleus, it's going to turn into a radioactive mess. We need a way to mathematically lock that chaos down.
We absolutely do.
We need a software layer to organize the rhythm.
Which brings us to the cryptographic core of multicode 6.0. The researchers merged this nuclear physics with high-level number theory, relying heavily on something called the Carmichael function.
Now, the Carmichael function defines cyclic processes in modulo systems. And for those of you who aren't cryptographers, modulo math is basically clock math.
That's the best way to explain it.
Just like the hours on a clock wrap back around to 1 after hitting 12, modulo math creates perfectly repeating endless cycles.
Traditional cryptography, like the RSA encryption securing your bank data right now, uses the Carmichael function to find the most mathematically efficient pathways for these wrapping numbers.
Okay.
But Multicode 6.0 does something radical. It takes this purely mathematical function and uses it as the exact equivalent of a physical resonance frequency.
Wait, really?
Yeah. The math dictates the physical rhythm, the precise period after which the vibrating samarium system returns perfectly to its original state.
And the source material highlights a very specific, almost magical number they use to generate these rhythms, 25001.
The number 2501 is the product of two prime numbers, 41 and 61.
Right.
When you feed 2501 into the Carmichael function, it generates incredibly complex overlapping cyclic structures. And those mathematical cycles happen to perfectly harmonize with the physical resonance frequencies of the samarium atoms.
The math perfectly overlays the physical matter.
Exactly.
But the code doesn't just stop at prime numbers. To optimize the signal and correct any errors that might pop up, say, if an atom decays, they integrate the Fibonacci sequence.
Yes.
Specifically, they use the Fibonacci number 89.
And we see the Fibonacci sequence everywhere in natural growth patterns, right? From the spirals of galaxies to the arrangement of leaves on a stem.
Yeah, it's everywhere.
By embedding this predictable, recursive mathematical pattern deep into the code's signal processing, the researchers dramatically increase the data's self-similarity.
Think of Fibonacci numbers like a highly predictable mathematical architectural grid. If you're building a bridge based on a strict geometric ratio and a chunk of that bridge collapses, you don't have to guess what the missing piece looked like.
Because the ratio tells you.
Right, because you know the exact mathematical ratio governing the entire structure, you can calculate perfectly how to rebuild the missing section.
Exactly.
In Multicode 6.0, if a segment of your data gets corrupted, the underlying Fibonacci grid allows the system to seamlessly reconstruct the missing information.
And to ensure all of this beautiful math actually holds up in the messy physical world, the researchers run everything through intense validation software. They use established physical libraries like ENDFB, BEAS.
Which sounds like an alphabet soup, but these libraries act like digital wind tunnels.
That's a great way to look at it. They use physical consistency codes programs with names like Checker, PhysCon, and PSYCHE to blast the theoretical math and ensure it doesn't break the actual laws of physics.
So they're stress testing it.
Exactly. These programs verify that the chaotic, natural constants of the samarium atoms translate perfectly into mathematically unbreakable cryptographic keys.
So the math checks out. We have unbreakable keys locking up perfectly rhythmic data, but we still have a massive missing piece to this puzzle.
Where to put it all?
Right. Where do we actually save the file? If the radioactive samarium acts as the processor and the modulo math is the software, what acts as the physical hard drive holding the data?
Well, the answer pushes us into the absolute extremes of modern physics. The document proposes using Bose-Einstein condensates, or BECs, as the ultimate storage medium.
A Bose-Einstein condensate is a bizarre state of matter. You create it by taking a cloud of gas and cooling it down to just a fraction of a degree above absolute zero.
Extremely cold.
At that extreme temperature, the atoms lose their individual identities. They blur together and start behaving as one giant, unified superatom.
Once you have that supercooled cloud, the text details a process called electromagnetically induced transparency, or EIT. This is how the data gets written.
How does that work?
Normally, this cloud of gas would be completely opaque to light, but researchers fire a very specific, precisely tuned control laser into the BEC.
Okay.
This control laser alters the quantum states of the atoms, essentially making the opaque gas completely transparent to a second specific frequency of light.
So they open a temporary optical window in the gas.
Yes. Then they send in a single photon of light that is entangled with an atom and carrying your encrypted data.
Right.
The photon enters the transparent gas. The moment it's inside, they shut off the control laser.
The window slams shut.
The gas instantly becomes opaque again. The photon's light literally grinds to a halt inside the cloud. The optical data carried by that photon is immediately transferred and mapped onto the collective quantum spin states of millions of supercooled atoms simultaneously.
The document notes that the accuracy of this data storage is over 95%. And the data can be preserved in the cloud for periods 2 orders of magnitude longer than the original duration of the light pulse.
It's incredibly efficient.
The entire cloud of atoms acts as one massive, perfectly coherent harmonic oscillator. But, okay, let's unpack this. I have a major problem with the logistics here.
Let's hear it.
The source material lists energy efficiency as one of the major pros for this multi-code system. The logic is that resonant systems, like a pendulum swinging in a perfect vacuum, require almost zero external energy to keep moving once they're started.
Right, that's the theory.
But a Bose-Einstein condensate requires cryogenic coolers and high-powered lasers running constantly to maintain a temperature near absolute zero.
Yes, it does.
Doesn't the astronomical non-stop energy cost of cooling the hard drive completely cancel out the supposed efficiency of the resonance?
It is the central paradox of the system, and the text openly acknowledges this as the primary contra, or limitation. The enemy of this system is decoherence and thermal noise.
Heat is the enemy.
Exactly. Maintaining a quantum state across millions of atoms requires extreme, energy-intensive isolation. Even a stray magnetic field, or a microscopic fraction of a degree of heat, destroys the delicate phase relationships that the Fibonacci code relies on.
So the upfront infrastructure cost is immense.
And it really is.
So if the cooling cost is so prohibitive, why is this considered the future? Why do it?
Because the ultimate payoff is scalability. When you store your data inside a BEC, a single, carefully tuned pulse of light can manipulate thousands or even millions of atoms simultaneously.
Oh, wow.
It unlocks unparalleled parallel processing. Furthermore, it leverages a framework called second quantization.
Second quantization. In normal physics, we treat matter as the physical thing that holds data, and we treat light as the vehicle that moves it around, right?
Yeah.
But second quantization blurs that boundary completely. It mathematically treats the particles of light themselves as tiny, vibrating pendulums that hold data.
You're no longer just writing data onto a physical object. You're weaving information into the fundamental interactions between light and matter.
Which leads us to the final and undoubtedly most surreal section of this deep dive.
Yeah, things get a bit wild here.
When you combine nuclear radioactive decay, wireless quantum tunneling, near absolute zero cryogenic storage, and mass that wraps around itself eternally, the complexity stops being just an engineering challenge.
It evolves into something entirely different.
The researchers in the source material literally refer to this architecture as the monster concept.
They call it the monster code because it requires mathematical structures spanning up to 194 dimensions.
194 dimensions.
Yeah. Our human brains struggle to visualize anything beyond 3 spatial dimensions and the dimension of time.
Right.
Moving a data structure into 194 dimensions is pure, unadulterated mathematical abstraction.
Trying to comprehend a 194-dimensional data structure is like trying to read a novel, but instead of the words being printed on pages in a book, every single letter of the story is hidden on a different planet scattered across the galaxy.
That's a perfect analogy.
To a standard classical silicon computer that is pure anarchy, is totally unreadable. But to a quantum system resonating at the exact right modular frequency, those 194 dimensions snap together.
They harmonize perfectly into a single, crystal clear note.
And the authors make some fascinating cultural comparisons here. They compare this 194-dimensional mathematical beast to famous literary monsters,
Like Grendel from the epic Beowulf.
or the wild, untamed Heathcliff from
Yeah.
Wuthering Heights.
They even compare it to the Ducati Monster motorcycle, which seems like a wild tangent for a physics paper.
I know, it threw me off too.
But it makes perfect thematic sense. The Ducati Monster is famous in engineering circles because it lacks a traditional body. The raw, structural frame is the aesthetic of the machine.
Oh, I see.
All of these comparisons represent an underlying, beautiful anarchy that defies traditional mechanical or social order.
So in information theory, the monster code represents a state where the density of the information is so extreme, the lines blur entirely between the subject, the data you are trying to store, and the object, the medium you're storing it in.
Exactly. The data actually becomes the matter.
So pulling this out of the theoretical realm, what does mastering this monster code mean for the future of technology?
Well, if we connect this to the bigger picture, harmonic oscillators don't just exist in cold clouds of gas. They govern the physical world.
Everywhere.
They dictate the torsion vibrations of complex molecules, like ethene. If we master multicode 6.0, we aren't just building a better hard drive.
What are we doing?
We're learning how to speak directly to biological and chemical processes in their native resonant language.
The source material extrapolates this into the concept of matter programming. The idea that you could alter the physical atomic bonds of materials in real time simply by feeding them the correct resonant data sequence.
They also theorize hyperresonant communication networks that use gravitational waves instead of electromagnetic radio waves to transmit data across the cosmos.
Gravitational waves, that's unbelievable.
And perhaps the most profound implication of consciousness interfaces.
Right, our brains.
Yeah, human neural networks, the way our brains fire, also operate on rhythmic, resonant electrical oscillations.
So if you possess a code that perfectly models multidimensional resonance, you could theoretically synchronize a machine directly to the rhythmic firing of the human brain. Let's take a breath and zoom out on the journey we just took. We started today talking about how simple and physically rigid a standard computer hard drive is.
And we went far beyond that.
We traveled through the jittery, never-resting zero-point energy of a teleporting quantum swing. We watched the protons and neutrons of radioactive nuclear waste battle it out in the scissors mode.
We mathematically locked that chaotic vibration down using the endless clock cycles of the Carmichael function and the self-healing architectural grid of Fibonacci numbers.
And finally, we froze that perfectly encrypted data into a cloud of transparent gas near absolute zero, creating a 194-dimensional monster.
It really represents a profound, fundamental shift in how humanity interacts with information.
And for you listening, this isn't just a thought experiment. It matters because our global hunger for data is rapidly exploding beyond the physical limitations of silicon.
We can't keep using traditional chips forever.
No, we can't. The future of human knowledge, the very concept of being well-informed, might rely entirely on this kind of extreme physics. We're looking at a future where data isn't just etched onto a fragile chip, but physically, permanently resonates with the deep frequencies of the universe.
Which leaves us with one final, provocative thought to consider long after you finish listening.
What's that?
If multicode 6.0 relies on things like the naturally occurring Fibonacci sequence and the inherent harmonic frequencies of atoms to achieve perfect data transmission, are these scientists actually inventing a new code? Or are they simply building a microphone sensitive enough to finally let us hear the operating system the universe was already written in?